In section 1.3, we're going to be looking at subspaces of vector spaces. And as you can probably imagine, it's a space or a smaller space of the vector space itself, just as subsets you would relate to sets. So we're going to start off with the definition of a subspace. So the definition. So a subset U of V is called a subspace of V if U is also a vector space. And we use the same addition and scalar multiplication as on V. An example would be if V here was F3, right? This is V. U, our subspace, would be this set. And you can probably visualize what that looks like. If we're in F3, you may imagine a space, a three-dimensional space. U here is a two-dimensional space, which would be pretty much a plane, right? So here's a picture of kind of that what that would look like. Here we always do have to include the element 0, the 0 vector. 0 always has to be included in our subspace. And we're going to be looking at a theorem that helps us verify or be able to tell whether a subspace is a subspace or if it's actually just a space that is gibberish and doesn't fill the definition. So we're going to go on with a theorem. And these are the three conditions for a subspace. So a subset U of V is a subspace of V if and only if U satisfy the following three conditions. First one is, as I just said, U is in our subspace, right? So here I put in red in the picture, 0 has to be in there. Our additive identity. The other one is that our elements should be closed under addition. So for every U and W in U, U plus W should also be in U. The third one is closed under scalar multiplication. That means if A is an element of F and U is in U, then the product, the scalar multiplication A times U, should be also in U. What are those conditions? The conditions for a subspace? Well, we can prove that. So first, we're going to prove one direction. If U is a subspace of V, well then U satisfies the three conditions above by definition of vector space. Right, so that was a pretty easy one, but the converse takes a bit more work. So the converse says, suppose U satisfies the three conditions above. We need to show that U is then a subspace of V, right? So the first condition above, which is a 0, ensures that the additive identity of V is in U, right? So we got that. The second condition ensures that that addition makes sense on U, right? We're assuming this condition here. And the third condition ensures that scalar multiplication makes sense on U. And we can use these conditions for the proof. So for example, if U is in U, well then negative U, which is the same thing as -1 times U, is also in U, right? Because A, we can just call A -1 there, and then multiply by U, and it'll be in U. So this tells us that every element of U has an additive inverse in U. And the other ones, the other properties, the other parts of the definition of a vector space, such as associativity and commutativity, are automatically satisfied for U because, well, they hold in V, so they must hold in U as well. And this shows that U is a vector space and hence is a subspace of V. Right, so these are the three main conditions, 1, 2, and 3. Three main conditions for a subspace. Examples of subspaces. If B is an F, this is our U here, all the way down here. Actually, I'm going to erase it so we can see a bit better. This set where x3 is always equal to 5x the sub 4 plus b. This is a subspace of f4 if and only if b is 0. So only if this holds, right? We can't have any other number for b. We can't have 4. And it's a good exercise to verify that on your own. But again, the three conditions are what? Well, that we have an additive identity, it's closed under addition, and scalar multiplication. So we can verify using those three properties. Another example of a subspace is a set of differentiable real valued functions on R, and that is a subspace of R to the R. Right, and you should probably remember those properties from calculus for that example. But again, get an exercise to verify on your own. The last one is the set of all sequences of complex numbers with limit 0 is a subspace of C, this infinite dimensional space of the complex numbers. So why? Well, because the additive identity is there, namely the 0 sequence. Those sequences, we know we can add sequences, and it's just another sequence. If you remember from maybe a beginner's analysis course or calculus, if you add two sequences, you can add the limit. And same thing for scalar multiplication. You multiply the sequence by a constant. The limit will be its same limit times that constant. So again, those three conditions are really important to verify that something is indeed a subspace. Okay, moving on. We get the actually, sorry, ignore the definition. Before I even uh, state the definition, I just want to point out that the 0 element, the set 0, is the smallest subspace of V, and V itself is the largest subspace of V, right? Also, the empty set is not a subspace of V. Why? Well, because a subspace must be a vector space, so it must contain at least one element, and that element should be the additive identity, which is 0. So it's just something to point out. Also, you can, for example, if we had the vector space R3, well, R3, all the subspaces are all the planes you can make that pass through the origin. Similarly for R2, right? The vectors, the subspaces of that is all the lines you can make that include the origin. The origin has to be included in there. These lines aren't passing through the origin, but they do have to pass through the origin for them to be a subspace. Also, you could just include the 0 element and it'll become a subspace as well. But now we can move on to sums. So could you add vector spaces? Well, if U1 through UM are subsets of V, the sum of U1 through UM, denoted as it shows here, U1 plus dot 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 all the way to UM, is a set of all possible sums of elements of U1 all the way to UM. So for example, so here U1 plus UM is equal to this set. So U1, which is in U1, U2, which is an element of U2, U3, element of U3, so on and so forth. All possible sums of those elements are this sum here. That's how we define the sum of spaces, of subsets of V. So again, we can look at examples. So suppose U is a set of all elements of F3 whose second and third coordinates equal 0. And W is a set of all elements of F3 whose first and third coordinates equal 0. So it shows there in set notation, maybe that helps us see it a bit clearer. This is what we're calling U. W is down here. And if we were to add those two subspaces, we would get something like this. So again, here X could be any elements of F. Similarly, Y over here can be any elements of F. We just add those, and now it becomes this new space, U plus W. Okay, now we go on to a theorem that says, suppose U1 all the way to UM are subspaces of V. Well, then the sum U1 plus dot 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 all the way to UM is the smallest subspace of V containing U1 all the way to UM. And again, this proof has, I guess, two steps. I'll point them out. But it's a pretty straightforward proof. So first, it's easy to see that 0 is an element of this sum, U1 plus dot 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 all the way to UM, and that U1 plus all the way to UM, the sum, is closed under addition and scalar multiplication. Right, and why are we doing that? Well, because now we can see that this is really, well, a subspace of V. Right, the three conditions are met. Okay, so here I state clearly U1 all the way to UM are contained in U1 plus dot 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 all the way to UM. And why is that? Well, just consider, like, for example, small U1 plus dot 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 all the way to UM, right, where each U1 is an element, where each UJ is an element of UJ. So U1 is an element of U1, U3 is an element of U3, so on and so forth, right? UM is an element of UM. Well, to see that all of these, each of those subspaces are contained in the sum, just pretty much let all the other elements here equal 0. So for example, if I wanted to show that U1 was in the sum, U1 plus UM, I just have all the sums dot 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 all the way to Z0, where 0 is the M. Right, I can have all possible sums here, and that will equals the subspace U1. Similarly, you can do the same thing for U2. You can make that U2 and we can make the 0. And now we show that U2 is in the sum of U1 all the way to UM. So that's why we say, well, clearly U1 all the way to UM are all contained in the sum of those spaces. Give me 1 second to erase here. Okay, so every subspace of V containing U1 all the way to UM also contains the sum. And why is that? Well, because subspaces must contain all finite sums of their elements. Right? All of them. All finite sums of their elements. What does that tell us? Well, that therefore, the sum U1 all the way UM is the smallest subspace of V containing U1 all the way to UM. Right? And what I said, that there's two steps here that I'd point out, is just pretty much showing, here I'll cut it in half. One, that the sum of U1 all the way UM is a subspace. So this up here is showing that the sum of U1 all the way UM is a subspace. And the other one is just saying that the sum is the smallest subspace of V, containing U1 all the way to UM. Okay, moving on. We're going to define a definition which most linear algebra students have trouble understanding. It's pretty much the first concept where a lot of students have trouble grasping the concept of it. But before I do, I'm just going to note that sums of subsets, this may make it easier to understand. Sums of subspaces, in theory, of vector spaces are analogous to union of subsets in set theory. Right, so given two subspaces of a vector space, the smallest subspace containing them is their sum. Right, so analogously, given two subsets of a set, the smallest subset containing them is their union. Right, so that's how you could think of sums of subspaces, as a union of sets. So every element of U1 plus the sum of U1 all the way to UM can be written in the form of U1 plus dot 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 all the way to UM, where each UJ is in UJ, right? I had mentioned that before. Well, we're really interested in the cases where each vector in this sum can be represented in this form in only one way, right? That means it's unique. And that's so important. Oh, I guess I spoiled it, right? But the question was, are there cases when each vector can be represented in the form above in only one way? Well, yes, there is actually. And it's so important, we actually give it the name. We give it the name direct sum. So suppose U1 all the way to UM are subspaces of V. Well, the sum of U1 all the way to UM is called a direct sum if each element of U1, of the sum of U1 all the way to UM, can be written in only one way, as this form, as a sum U1 plus all the way to UM, where each UJ is in UJ. And if it is a direct sum, instead of just the regular cross, we use the cross with the circle. And that denotes the direct sum. That says this is a direct sum, right? So if you need to, go ahead and read that definition a couple times more. You may be thinking, when is it not a direct sum? When is something a direct sum? So we're just going to look at a few examples. Here's the example. Suppose U is a subspace of F3 of those vectors whose last coordinate equals 0. And W is a subspace of F3 of those vectors whose first two coordinates equals 0. Right, so this is U and this is V. Then U plus V is actually a direct sum. Why is that the case? Well, in F3, for example, if we let F3 be the reals, the three-dimensional. Here, for example, an element in the reals, let's say 4, 7, and 12. Well, here, 4 and 7 come from U, right? This is an element of U. And V has 12. 0, 0, 12. Right? This element here of F3 or R3, we can only represent it with this element plus this element. There is no other way we can represent this 4, 7, 12 with U and V, with other elements of U and V. The only two elements that work are those two. That's why it's a direct sum, because the way we represent it is unique. Okay, so I'm going to erase this to make space. A non-example, just so we can kind of see what isn't a direct sum, is if we let U, U2, U3 be those sets that we see there. And U1 plus U2 plus U3 is not a direct sum. So if you want, go ahead and pause. You can try to work it out, try to see why something would not be a direct sum, why this would not be a direct sum. But I'll show you now why this is not the case. Right, so the reason it's not a direct sum is because, say for example, I were to choose 0, 0, 0, element of F3, right? Well, this, I can actually, I'm going to write it down here so we have more space. 0, 0, 0 of F3. Well, we can write this as 0, 1, 0 plus 0, 0, 1 plus 0, negative 1, negative 1. Right? This is an element of U1. This is an element of U2. And this is an element of U3. But I could very well write 0, 0, 0 also as 0, 0, 0 plus 0, 0, 0 plus 0, 0, 0, where this again is in U1, this is in U2, and U3. So there's two different ways to write. Actually, I'm just showing two ways. There's actually a bunch of, if not infinitely many ways to show that 0, 0, 0 is not unique. Right? We can write it a bunch of different ways. So that's why that is not a direct sum. Okay, I'm going to erase this. I do think, so just as the sum of subspace was like the union of sets, there's something similar with the direct sum of subspaces. But let me erase this really fast so I can put it on there. Okay. Oh, I already gave you the answer. Uh-oh. I went a bit too far. Anyway, this the definition for direct sum is it requires that every vector in the sum has a unique representation as an appropriate sum, right? And this theorem that already popped up, this shows that when deciding whether a sum of subspace is a direct sum, we really only need to consider whether 0 can be uniquely written as an appropriate sum. That's all we need to do. So conditions for a direct sum, suppose U1 all the way UM are subspaces of V, then that sum of U1 all the way UM is a direct sum if and only if the only way to write 0 as a sum, U1 all the way to UM, where each uj is in uj, is by taking each uj equal to 0. This is I guess a lengthier proof, but it's neat and it's not really hard to follow. So let's go ahead and start with that. So because it's an if and only if, a biconditional statement, we do need to prove one side first. So we're going to first suppose that U1, the sum, U1 all the way UM, is a direct sum. Right? Well, then the definition of direct sum implies that the only way to write 0 as a sum, where each uj is in uj, is by taking each uj equal to 0. Right? 0 plus 0 plus 0, that should equal 0. So that's fairly, well, simple. It's as clear as it can be. The other direction, a bit more work, but not too hard to follow either. So now suppose that the only way to write 0 as a sum, U1 all the way UM, is by taking each uj equal to 0. Right, so now we're assuming this up here, and we're going to show that it's a direct sum. So to show you the sum of u1 all the way um is a direct sum, let a vector v be in that sum. Well, we can write v as sum, right? Where obviously u1, each uj is in uj. But we can write that vector as sum, as a sum. Well, to show that the representation is unique, suppose we also have v equal to v1, the sum of v1 all the way to vm. Right, so here we have v's, over here we have u's. That's the difference. And those two, we're supposing that these are the two different ways to write v. Well, subtracting these two equations, we get v minus v at 0, so that's why we have 0 on the left-hand side. On the other side, on the right side, we have u1 minus v1, so on and so forth, all the way to um minus vm. And because u1 minus v1 is in u1, and all the way to um minus vm is in um, well, this equation above implies what? That uj minus vj is equal to 0 for each j, right? So therefore, u1 is the same thing as v1. And that's how we showed it, right? We suppose there was two, but hey, indeed, they're actually the same one. So that's why we get that the sum is unique and therefore a direct sum. Okay, so just one more slide. This next theorem that I'm going to show gives a simple condition for testing which pairs of subspaces give a direct sum. Last slide. Suppose u and w are subspaces of V, then u plus w is a direct sum if and only if their intersection is the zero vector or the zero element. So again, by conditional proof, well, first we're going to suppose that u plus w is a direct sum, right? Well then, if u plus, sorry, a bit technical difficulties. First, suppose that u plus w is a direct sum. Well then, if v is in the intersection of u and w, well then 0 is equal to v plus its inverse, negative v, where v is in u and negative v is in w. And since it's a direct sum, we have that the unique representation of 0 as the sum of a vector in u and a vector in w, we have that v is equal to 0. So therefore, the intersection of u and w is just 0. So that completes the proof in one direction. But now the other direction. Now we're going to suppose that the intersection of u and w is just 0. We're going to show that this is a direct sum. Well, if the intersection is just 0, we're going to suppose that u in u and w in w added together give us 0. So what do we need to show? Well, we need to show that u is equal to w and it's equal to 0. Well, by the theorem in the last slide, the equation above implies that u is equal to negative w, right, which is in w. So therefore, u is in the in the intersection of u and w. Therefore, u is equal to 0, which by the equation above, right here, or by this one, we get that W is equal to 0. And that proves it. Um, Now, I do want to mention one more thing. And here we have it in box yellow. Just as I had mentioned before, I wanted to mention this previously, but I was getting ahead of myself. But the sums of subspaces are analogous to unions of subsets, right? We had already mentioned that. Well, the direct sum of subspaces are analogous to disjoint union of subsets. So no two subspaces of a vector space can be disjoint because both contain 0. So disjointness is replaced, at least in the case of two subspaces, with the requirements that the intersection equals 0. So that's how you can kind of think of direct sums, right? As disjoint unions of subsets. And the last thing I want to mention, I don't think I included it in a box, but when asking about a possible direct sum with more than two subspaces, we can't check. It's not enough to check that each pair of the subspaces intersect only at 0. Right? So, for example, U1 intersection U2 equaling only 0, U2 intersection U3 only equals 0, U1 intersection, that looks like it's an intersection. Intersection U3 is only equal to 0. This, checking them pairwise is not enough. And to see that, you can go back to an example we had done where we had a direct sum and check that these intersections give you only 0, but you'll see that U1, U2, and U3 do not form a direct sum.